Good afternoon. Thank you so much for coming today. Can you hear me all right? Or okay, very good. So it's really neat to be here, and it's especially nice to be here among all these terrific Columbia alumni who were a delight to work with at Columbia, and it's just terrific to see them so successful and happy here. It's our great pleasure to present our joint work. This is joint work with two PhD students from Columbia, Anna Pop and Junho Choi, in the Sustainable Development PhD program that we have representation from here today. What we're presenting on is a question of externalities from the combustion of coal. And before getting into the meat of it, I'd just like to say why I think this is an overarching and very important question. As you know, the use of renewable energy has been taken off very rapidly globally, right? And we've seen costs for wind energy and solar energy falling a lot. And the fraction of global energy that's being supplied by these renewable energy sources is up to 30%, which is really encouraging. On the other hand, energy demand globally has been going up very fast. And what that means is, in absolute terms, we're actually using more and more fossil energy. And so if you look at coal consumption, we sort of think of coal as sort of like the dying energy source. Coal consumption today is about 3 times greater than it was in the 1960s. Okay? So even though these fractions of our energy consumption are encouraging that we're using more renewables, the fact of the matter is, in levels, we're using a lot more fossil. And when we think about climate change and externalities, those things care about the levels, not like the fraction of our energy mix. And so this is a very worrisome trend that we're devising all these new uses for energy, right? And crypto mining is one of those sort of new uses for energy that we've managed to come up with. And so this is a paper focusing on the externalities of one of these new uses of fossil energy that we found, focusing on more localized effects. We have a previous paper looking at the effects on carbon emissions and global greenhouse gases. This is now looking at localized effects on populations in Pennsylvania. It's also very much work in progress. So I do encourage you, in econ seminar style format, please raise your hand, please interrupt me. This is not a well-coiffed, finely polished presentation, and so please just keep it informal, keep it constructive, and I'll be very happy to take your comments. Okay, so with apologies for showing you the American flag, the reason why I'm showing you the American flag is to say that America really likes crypto, especially now. Okay, so. Crypto, from an objective perspective, offers multi-dimensional benefits in terms of transaction speed, privacy, security, and decentralization. The mining of cryptocurrencies, revenues from that are estimated about $15 billion per year. The US is the number one miner globally of cryptocurrency, and Bitcoin included in that. And despite this large presence of crypto mining in the United States, we don't really know a lot about it. And we don't really know a lot about it because there aren't strong reporting requirements. It's not like there's a sort of census of manufacturers that requires you to report whether you're mining cryptocurrency or not. So there's a lot of inferences being made based on data. And one of the power plants we're looking at is not an admitted crypto miner. It just really behaves like a crypto miner, which will show you the sort of regression results for that. The policy context in the United States has been very favorable towards cryptocurrencies. US states in particular have very aggressive subsidies to draw in crypto mining to their jurisdictions. So for an example, Texas offers 10 years tax abatement and sales tax credits. Even New York, so even the more Democratic leaning states, if you see in this figure in the bottom left-hand corner, different prices per kilowatt hour are charged for different uses. And in New York State, you get the biggest discount if you are using energy to mine crypto. So we're heavily subsidizing crypto in the United States, whereas other countries like Sweden, where Simi just was, or China have much more restrictive policies on crypto. So Sweden has a 6,000% tax increase imposed on crypto mining, and China banned it in 2021. So there's just the massive diversity of policy responses to crypto mining. Under Trump, this is getting even stronger and more favorable at the federal level towards cryptocurrencies. Trump very much wants the US to be a crypto mining superpower and is doing that much more to stimulate the industry. This is just one of many recent stories talking about the federal government's injection of pro-crypto policies. As you may know, the main cost of crypto mining is power generation. And as the difficulty of mining progresses, more energy is required to mine crypto. So it's been estimated, and these are definitely estimates with large standard errors, that in the United States now, crypto energy demand is roughly like Los Angeles or New York City. So we're adding like one of our biggest cities to the grid and using that to mine crypto. In the United States, the grid is currently 60% fossil. It's been estimated that crypto actually tends to use a disproportionate amount of fossil, something more like 85%. What are we going to do here in this context of a growing crypto-friendly environment in the United States? Well, we're going to look at local pollution impacts of crypto mining at the electricity generator level. We're going to use new U.S. administrative data set on daily labor market outcomes. So in general, there's some very well-trodden data sets that labor economists use for the United States, like the current population survey or the American Community Survey. This is a new data set that has some really nice advantages that combine well with our identification strategy. And the key thing for us is we want to be using daily variation in the incentive to mine cryptocurrencies. Because when the crypto price changes, and it changes a lot, as you probably know, the incentive to mine crypto changes because you're rewarded for mining cryptocurrency in Bitcoins. Okay, so if the price is high, you have more revenue when you mine a new Bitcoin. So given those daily fluctuations in Bitcoin mining incentives, we want to marry those to a data set that also has daily variation in how much people are working, et cetera. And that's what this new administrative data set provides. That said, it's not a representative data set of all workers in the United States. It's for people who are paid hourly, and people who are paid hourly in the United States tend to make lower wages. And so it's going to be very heavily concentrated in like food and beverages, retail, lower wage workers. So that's whom we're going to have our estimates for. We think ours is the first paper to look at the effects of Bitcoin-induced pollution on labor market outcomes. We look at Pennsylvania in particular. Why looking in Pennsylvania in particular is because in this environment where reporting of data is so imperfect, we have a Bitcoin miner that's self-identified. They're happy to say we are a vertically integrated on-site Bitcoin miner. So they have the power plant and they have the servers mining Bitcoin all in the same place. So just from the information perspective, that's why we're focused on Pennsylvania. Additionally, they're not, at least in recent years, supplying electricity to the grid, okay? And because they're not supplying electricity to the grid, all of their mining activity is additional. It's for the purposes of Bitcoin. So we can think about pollution coming from those plants as pollution that would not be occurring in the absence of Bitcoin. So we have two coal-fired power plants in Pennsylvania with on-site crypto mining. Scrubgrass facility in Panther Creek, they're both around 80 megawatts, which is not that big. They're relatively small potatoes. still, we're going to, despite being relatively small potatoes, we're going to be able to find some substantial externalities from their operation. These are not the most efficient coal-fired power plants. Back in 2012, the Union of Concerned Scientists listed these two power plants in particular as ripe for retirement. In terms of heat rate, the efficiency of their conversion of coal to energy, they're much less efficient than the average coal plant in the United States. And when these plants took on Bitcoin, the news from the time, had the headline that you see here: Bitcoin miners revive a dying coal plant. So we think these are additional emissions that would not have occurred in the absence of Bitcoin. If you don't find that sort of narrative so persuasive, well, we're going to use the Bitcoin mining incentives as our instrumental variable, our Z, right? So we're only going to be using variation in Bitcoin mining incentives, at least at the start of this talk, and therefore everything in terms of pollution that's coming from Bitcoin mining incentives is pollution that's occurring thanks to Bitcoin, if you believe the validity of our instrument. Additionally, and this is where it gets a little bit more like sleuthing or forensic economics. So there's this, nice tradition in economics summarized by this paper from now 13 years ago by Zitzweitzer. Forensic economics is, using data to detect behavior that people would otherwise like to conceal. And that's what we're going to be doing with this Northampton generating plant. This plant was rumored to have emerged from bankruptcy to mine Bitcoin. It, unlike the previous two plants I mentioned, has a very typical heat rate compared to coal power plants in the US. So it's more representative of coal plants generally in the United States. It also consistently has one of the strongest first stages in terms of how electricity generation and pollution respond to daily variation in Bitcoin mining incentives. It also has the closest EPA pollution monitor. From like a power perspective, but not from a welfare perspective, we like it because it has the highest population density near the power plant. These sub-bullets here talk about rumors that this is a Bitcoin miner. It also has a higher nameplate capacity at 134 megawatts. And then finally, it's only 70 miles from Manhattan. So you can think about that's maybe not so great to be near yet another big population center. But given that I don't know anything about, the practicalities of coal-fired power generation, we took a flyer and emailed Northampton and said, hey, we are some, PhD students interested in coal-fired power plants. Would you give us a tour? And surprisingly, they said yes. So a couple weeks ago, we drove to Northampton to check out their facility. And so we have Junho here over on the right, a couple of other sustainable development PhD students. And then this is Lauren here, the person who's the emissions person at Northampton Generating, who gave us a very comprehensive 3-hour tour of her power plant. So that was terrific. We learned a tremendous amount, and not all of it accorded with our expectations. Here we are in the control room, where they were very friendly, and that's Junho looking very surprised, I guess. What they're doing there in the control room is responding to real-time prices in electricity. Okay, so they're ramping up their generation roughly by 10 megawatts an hour in response to price changes. So here are some things that we learned during our visit a couple Thursdays ago. There was no on-site server farm. Okay. Now they may have hidden it from us. We didn't go into every building. We're not like trained inspectors. We're just faculty and PhD students. So that was a bit of a surprise to us that wasn't obvious and that wasn't being admitted. They did say something which we had to be very polite about when they said it so proudly, is that they receive very substantial green energy subsidies at this power plant, and they would not be economically viable without these green energy subsidies. And the argument that they made with the state of Pennsylvania is because they're burning coal refuse, stuff that was dragged out of the coal mine over the last 100 plus years, because they're like reducing these piles of coal, that somehow is a green or pro-environmental activity. So I think that's a very dubious claim, but they managed to make it with the state of Pennsylvania. It's one that Joe Manchin has also made in West Virginia as well. So when a Pennsylvania consumer of electricity selects like green energy, they are literally selecting burn coal from a power plant like Northampton, which was very, very surprising to me. And it's in the context of strong subsidies for what turns out to be crypto mining activity in the United States that otherwise might not be viable. So no surprise, the crypto miners are landing in Pennsylvania because they have a very favorable treatment of burning coal if it's coal refuse coal. Northampton responds extremely attentively, and we met the guy who responds extremely attentively to both the day-ahead price per kilowatt hour and also the real-time price. So there's sort of two components of price that they respond to. As mentioned, they can ramp at roughly 10 megawatts per hour. That is a surprise to me. Again, I don't know anything more than the average person about coal-fired power plants, but I had sort of imagined coal-fired plants would just sort of churn at a steady rate. And here they are ramping up and down, which is something I associate more with like natural gas-fired power plants, not coal-fired power plants, but they're doing it at the coal-fired power plants too. The price that they're responding to is an extremely local electricity price. So what we suspect is going on, but this is like a TBD part of the story, is there's local Bitcoin mining activity that's responding to the Bitcoin price that in turn is sending a price signal to this particular power plant, which they in turn are then responding to. But this is like the inferential forensic economics part of it, is we don't have that link other than the statistical link that we're drawing. As an aside, we've tried that trick in other places of looking to see if we can infer some Bitcoin miners. And we most recently tried that in China because, yes, China banned crypto mining, but there have been rumors that China has been picking it back up. As you probably know, China has a lot of excess capacity in its power generation sector. And despite that, it continues to build coal-fired power plants, which is a little bit or a lot strange. So given that they're not operating all the time, there'd be an incentive for them to respond to Bitcoin mining incentives as well. And essentially, we didn't find that. We don't find them responding to at least the daily variation in 2022 in China. So we think this Northampton Bitcoin miner is responding extremely adeptly to daily movements in price. And this guy who's sort of slouched in the chair, that's Jerry. He's the one that's responding in real time. How much should Northampton be generating? How much coal should it be burning in response to fine movements in the price? And since Sime mentioned that we have 4 daughters, I did one bad thing, which was pretend that one of these students was a sustainable development student who wasn't. She's actually a daughter that was just snuck in there. And she was very nervous about being snuck in there. Like, what if they ask me questions about sustainable development? She's a first-year college student in engineering and said, they're not going to ask you any questions. But she had a really fun time visiting the power plant. Okay, so Northampton and Sydney, do I go till when?
You have till 2, but you want to leave some time for Q&A. So.
Okay, perfect. Okay, very good. Northampton, this is just showing over time the number of unique workers in our labor force data set. You see their strong seasonality, and maybe this is not so surprising in these low wage and sort of service-oriented occupations and industries. This means that when we're thinking about labor market impacts from Northampton, we tend to have roughly around 500 workers that we're looking at within 20 kilometers of the Northampton generator. So our data that we're very, very excited about are going to be first the Bitcoin mining incentives. So we're looking over roughly 3 years. So that's 1,034 daily changes in Bitcoin mining incentives, starting from 2021 to up until last summer. So that's one global data set, right? So when we're looking at the China power plants, we're using those same prices. And that's good and bad. It's the variation we have, but also it's unlikely that these little power plants in Pennsylvania are doing things that are affecting those prices, since it's a global price. So we're sort of happier thinking that that's exogenous. Additionally, we have data from essentially one ambient air quality monitor that happens to be fairly nearby. And that's sort of measuring pollution in the community or neighborhood, so to speak. We also have the data from the power plant itself, which is reflecting how much SO2, how much NOx, how much carbon is coming off of the stack of the power plant. Okay, so that's in the environmental econ literature, that's referred to as CEMS data, which is continuous emissions monitoring system data. Those are the gold standard for data, and they get in huge trouble if they mess with those. And on our tour, we got to see sort of the CEMS monitoring operation, and they take that part very, very seriously, and they're actually very proud of being within environmental guidelines for how much SO2, et cetera, they can emit. So we have a very good measure from each of our 3 power plants of how much pollution they're emitting to the atmosphere. The labor market data, they come from this firm called Homebase. And what Homebase is, it's a payroll tracking firm that's just very successful in selling its administrative software to small businesses. Over half of US workers are paid hourly. And so from this software tracking data, we have information on hours worked, wages paid, a unique identifier for each worker, that sort of thing. So this particular home-based software is used by 100,000 small businesses across the United States. Convenient for our purposes, the data are available at the daily level back to 2016. And we know the zip code of the employer. Okay, so that's pretty good geographic identification, which is going to, turn out to be important for both mapping proximity to the power plant. But then when we move forward and use an atmospheric dispersion model to see where the SO2 is going when it's released from the top of the smokestack, we'll be able to use the richness of where zip codes are relative to the power plant and the prevailing wind direction at the time that the pollution was emitted. But we're going to start in a very basic fashion of just looking at workers who are located within 20 kilometers or about 12 miles of the power plant. Consistent with the theme of praising Columbia University, which probably you haven't heard a lot of recently, but this is a very pro-Columbia presentation. Hannah Farkas is a PhD student who will be coming on the job market this coming year. She's the one that uncovered these data. So her job market paper for the fall and this paper here are the first 2 known uses of this payroll administrative data on daily labor market outcomes, which I think are pretty exciting.
So did you have to purchase this or?
Yes, so we just had to nag them. And then they gave it to us for free, which is very strange, right? Here's the universe of our data, and they're very lovely. So maybe it'll get tougher, but for now it's it's a good time to be asking. So if you go to their website, you can see the different plans. You as a small business, if I had a small business, I would have no better idea than using home-based administrative software. It's very cheap. It's apparently very easy to use, and it's used by 100,000 businesses in the United States. So we have lots and lots of workers who are covered nearby. So what do we see in these data set? We have a unique company identifier. We have the location down to the zip code level. We have a unique employee identifier. So that's going to be useful for when we want to think about controlling for worker characteristics, looking at variation within each worker, that type of thing. We know the industry. We know when each employee was hired, how much they make per week. We know how many hours they work each day, and that's going to be our main measure, is how many hours do they work each day. The hourly wage rate is also going to be a subject of our analysis, but it's actually not calculated or derived from the hourly data. It's derived from the weekly data divided by the number of hours per week. So it's not going to be sort of a very elastic responder to like daily variation in pollution or something like that. Here is just some basic descriptive statistics on the home base data set. We have overall, if you look at the red numbers, we have about 8,000 workers. They sort of come in and come out of our sample over time. The mean number of days worked at a job is 77. Okay, so these are relatively short spells, and so in that figure I showed you for Northampton with 500 workers, we sort of maintain 500 workers, but they're not the same workers over time. They're new workers coming in and old workers going out, that sort of thing. The wages are low, so the average hourly wage is like $14 US. And you'll see that like P1, that's the first percentile, that's really, really low. And so like this 2.5 or 6.5, these are in industries where tipping is common because there's a 7.25 minimum wage. But for some of our workers, the use of tips is going to be really important. In terms of their distribution across industries, F&B stands for food and beverages. If you look at the middle bolded number, that is the number of unique workers. So there's roughly 3,300 unique workers in food and beverages. And you see, again, that their P1 is down at 1.34, and even the 25th percentile and 50th is below the minimum wage as well. Next up is amusement, gambling, and recreation, followed by social assistance, and then smaller types of industries as well. But this is to give you a flavor of the type of workers who are in our data set. These are low-wage workers working in relatively short jobs. So like if you, like I, am interested in sort of the environmental justice perspective, we're looking at a very interesting subpopulation of low-wage workers. And this is it for the smaller ones. We have healthcare services, which I'll highlight here because something that we're not able to do well here, but might be able to in future work where we can sort of pin down the labor demand curve, is healthcare services are in some sense going to have competing effects. We might think that when it's more polluted and that's harmful to health, that's going to be like a leftward shift in labor supply. But on the other hand, if you're in healthcare services and there's a positive demand shock, maybe that force will win. So that's going to be the forces at play for the more health-related outcomes. And I'll say as an aside, we initially tried to get health data to do this project from the state of Pennsylvania because there are daily hospital discharge information, and we tried repeatedly with them, but for confidentiality reasons, it's not something they were willing to part with. So we moved on to the labor force outcomes we're showing today. This is just the frequency distribution of wages, showing you the black vertical line at $7.25 an hour, the minimum wage for Pennsylvania, and you see that in industry without tips, over on the right-hand side panel, we have workers with wages kind of as we'd expect them, whereas if tips are more important, then we have more mass to the left of the minimum wage. Okay, our Bitcoin variables. So as you know, the Bitcoin price has moved around a lot. We measure it in thousands of US dollars. So the average Bitcoin price over our sample period is something like $37,000. per Bitcoin, and it has moved around quite substantially, which I'll show you in a second. And then we have a bunch of other Bitcoin variables, which empirically are going to turn out to be less important in our analysis. But one of the things that's more important is the mining difficulty. So if the price is high, it's more likely that other miners are going to come online and try and mine the Bitcoin and realize that high price. And so what difficulty and hash rate are doing are measuring the challenge of successfully mining a Bitcoin. So hash rate is picking up, in particular, how many other people are trying to mine Bitcoin at a point in time. And difficulty is measuring the complexity of the problem that's being solved. And that difficulty has been changing over time to generate a certain supply of Bitcoins over time. So those are other factors that power plants might consider besides just the price. In terms of emissions, Northampton and Panther Creek are relatively similar. If you look at sulfur dioxide emissions, they both have means around just under 1 in terms of tons per day, and standard deviations around 0.7. Scrubgrass is the dirty one. Scrubgrass has a mean of 3 tons and a kind of a fat right tail of emissions as well. Fortunately, Scrubgrass doesn't have a lot of people living near it. So the rest of the presentation outline, I'll give a little Bitcoin background and a very brief literature review, talk about some OLS results, ordinary least squares, and then show you the first stage. The first stage in the IV setup is looking at how pollution responds to Bitcoin mining incentives. Then the IV results will be what do we see in terms of labor market outcomes, and how do these respond to pollution when we use Bitcoin incentives as the instrumental variable. Briefly, I'll do an event study analysis. That's going to be leveraging different aspect of the variation, which I think is also interesting. It's going to be less focused on the Bitcoin incentives piece of that. And then I'm going to sort of ask you guys about sort of where we should go next. We've started with these 3 power plants in Pennsylvania. As mentioned, we can sort of see which other power plants in the United States are responding swiftly to Bitcoin mining incentives, and nothing prevents us from looking at the same data for these other power plants as well. So that's one direction we could go. But one thing we often tell ourselves or tell PhD students is, just because you can do something data-wise doesn't mean you should do something data-wise. And so maybe we need to be disciplined and say, we've learned a fair bit here, and maybe it's time to write up the paper. Which I apologize, there's no paper to send to y'all just yet. This is the work in progress. And the aspect of this work that's the most work in progress is this AirMod model, which is an atmospheric transport model, which uses features of the topography, wind direction, wind speed to see where the emissions from the plant are going to over time. And then I'll conclude with some next steps and then take questions. Okay, so Bitcoin mining basics. Bitcoin miners are validating transactions. They're providing a service to the Bitcoin network. And when they do that, if they are the first to solve a complex mathematical problem known as hashes, then they're rewarded in Bitcoin. And the complexity of that hash has been increasing over time. So you're rewarded in Bitcoins, and you receive some transaction fees as well. Drivers of Bitcoin mining activity include what I've mentioned before, like Bitcoin price, since that's your revenue, the mining difficulty, and other aspects of things like time to confirm a transaction, Bitcoin futures prices. So you might think, okay, I have costs of ramping. Maybe I care about not just the price today, but also the price tomorrow. And for a while with this project, we were doing sort of a machine learning exercise where we were regressing pollution on all of these variables and their interactions and their higher order terms, right? Like just like a hot mess of these variables. And that was fun. You can do that. And, Angus would maybe be okay with that, is you're sort of like hacking the first stage in some sense, because we just want to predict pollution using these exogenous variables. So we had some very complicated first stages going on. At the end of the day, what performs probably the best is just using Bitcoin price, linear and quadratic. Okay, so like Bitcoin and Bitcoin price squared. This other stuff, yes, sometimes it's helpful, but we get some of our best, strongest F stats when we just use Bitcoin and Bitcoin price squared. Maybe these power plants are fairly, single-minded in what they're following, despite maybe opportunities to make greater revenues. Okay, yeah. So on we go to some figures. Here's the Bitcoin market price over time. This again is in thousands of dollars. So we had some heady days in 2022, up or over $60,000 per Bitcoin, and then dropped to less than a third of that. And then later in our sample period, it's back up above $60,000. We are going to have like a cubic polynomial in time. Okay, so if we have a cubic polynomial in time, we're not leveraging like this peak trough peak thing, right? We are leveraging deviations from that cubic polynomial. Okay, so yes, there have been some wide swings, and those wide swings are going to have real impacts on the amount of generation. But for identification, so as not to be confounded by other things that are changing over time, whatever, COVID, anything else, we're looking at higher frequency movements. This is the mining difficulty of how complex the problem to solve is. And that's gone up by a factor of 4. So other things equal, like if you don't change your servers, et cetera, it's gotten 4 times as hard to solve the problem, which means 4 times as much energy over time. So that's a factor that's causing increased energy demand. This is the only figure we know of showing where Bitcoin mining activity is occurring. This is from our previous paper looking at the carbon emissions effects of Bitcoin mining. And what you see is the US has been coming up since 2020, 2021 in terms of its global market share. And in China, it's estimated that when they banned crypto mining, it fell to 0, but then came back up to around 20% of global Bitcoin mining activity. Unfortunately, this figure does not continue past 2022 because the data stopped. Okay, it's not like we're lazy and we just didn't update the figure. It's actually the case that they no longer make that available. So it's less known now where Bitcoin mining occurs than it was a couple years ago. Here is a map of Pennsylvania, and it's showing our brown stars are our 3 power plants. So Scrubgrass, the especially dirty one out in western Pennsylvania, Panther Creek in eastern Pennsylvania, and Northampton, which is the larger of the power plants that has more people right around it, and furthermore has an EPA pollution monitor nearby it. That's the red circle that also says Northampton. So we have a check on the SEMS data coming from the power plant in having this EPA pollution monitor right nearby. Here's a distribution of heat rates by power plant in the United States. So this is for all power plants, and you can see that the brownish color is for coal and the distribution of the heat rates. The vertical dotted lines are for our 3 power plants. The ones over to the right are Panther Creek and Scrubgrass. So they're out sort of getting into the tail of the distribution of heat rates for power plants in the United States. So they're relatively inefficient. They require a really high heat rate. Whereas the blue dotted line that's more towards the left, that's our Northampton power plant, which is pretty close to right in the middle of the distribution for coal-fired power plants. So that's another reason why we like Northampton. Interestingly, and I mean, if you're a marketing person, maybe this is what you do for lunch. Stronghold Digital Mining has some very bold environmental claims about its mining activity. It is very proud of its emphasis on environmentally beneficial operations. You see this, throughout its corporate reports, through its quotes in the news media, etc. And again, it's motivated by this so-called service of working on these coal piles. Okay, so eliminating mining waste, converting waste to power. And they have been successful in this argument because Pennsylvania has been increasing the coal refuse reclamation tax credit over time, making it a very lucrative market to burn waste coal. Stronghold was acquired by a Canadian firm in March 2025. So sort of the information flow about these power plants has changed over time, but it's being acquired by Bitfarms Ltd. So by a global conglomerate that's mining Bitcoin. Okay, so that was sort of Stronghold's claim to environmental benefits. If you look at their violations over time, both Scrubgrass and Panther Creek have been violating air quality standards. Controversially, Panther Creek and Northampton as well burn what's called TDF, tire, like they're literally burning tires there, which has a whole different set of emissions that come about because of that. It has a lot of energy content in it, so it's used as a supplement to change the BTUs of the fuel source being currently used. Despite burning tires, they don't have to change anything in terms of the regulation because they're already an established source. So that's sort of a wrinkle in the laws governing fuel use. Yep.
So is this tire real tire?
It's tires. It's literally tires. Yeah.
So they burn retired, no longer used tires.
They burn used tires.
Oh.
Yeah, and it's has a very noxious set of stuff that comes out from it. Yes, it's as bad as it sounds, which is why they had to have the acronym TDF, because it doesn't sound as bad as tires. Yeah, but they're literally burning tires. Northampton also has what they call a charity burn. Like if you show up with 5 tons of something you want burned, they'll burn it. So it's it's the Wild West, and it's 70 miles from Manhattan. So 100 residents of Carbon County, it literally is called Carbon County. Sounds like the Onion version of this paper, but it's Carbon County in Western Pennsylvania. Residents have sued because of the burning of tires, the use of TDF, noting, as I guess I'm pretty obviously persuaded by their argument that this plant has been receiving strong tax credits from Pennsylvania, and as their lead attorney says, they are causing a tremendous amount of toxic waste in the air, water, noise pollution for people who live nearby, and the worst, Pennsylvanians are paying for it through these subsidies, right? Like they wouldn't be viable without these subsidies. Okay, so those are the two sides. Stronghold thinks that they're doing environmental benefits, and state government in Pennsylvania seems to think they're doing environmental benefits because they subsidize it. Whereas I think a more dispassionate look at it says that this is power plants that should not be operating that are operating. Okay, so you probably know that there's a large literature on health effects of air pollution. There's a somewhat smaller literature on the labor market effects. Probably the first big paper in that space is by Rima Hanna and Paulina Oliva in the Journal of Public Economics. They were looking in Mexico City at the closure of a big oil refinery, which caused a 20% reduction in sulfur dioxide levels in surrounding neighborhoods, I believe within 10 kilometers. They did not have like the daily data that we have. They were looking at weekly data, and they find that when this refinery closed and sulfur dioxide emissions dropped and concentrations dropped, there's about a 3.5% increase in hours worked. And that there was a lagged effect whereby effects appeared the following week. So they're looking obviously at a very different context, but additionally a different, temporal aggregation. That's not something we've done yet, is to look at the weekly level, because we're sort of in love with our variation that comes at the daily level, but it's something we could consider doing, but it might be more subject to confounding. Josh Graf-Zivin and Matt Nidell are looking at a very different subpopulation of agricultural workers in California, and looking at effects of pollution, not on sort of the extensive margin of labor supply, but instead on how productive people are on the job. And so they make the argument that labor supply of agricultural workers is highly inelastic in the short run. They just show up and they're ready to work, and that show up decision does not respond to air pollution levels. So because they have this piece rate compensation, they're very good data on how much each worker is able to pick in a given day. And what they find is ozone, even at modest levels, so ozone at levels well below the federal air quality standards for ozone, have a negative impact on productivity with roughly a 5.5% impact on labor productivity. So there are these two things that could be going on, both the extensive margin of labor supply, but additionally how productive you are when you're on the job and facing more pollution. Again, this is ozone and that is SO2, but these are sort of the greatest hits in this literature. There's also this recent paper by Eric Zoe and co-authors in Restat that's looking at wildfire pollution. And they make the argument about wildfire pollution that it's becoming an increasing share of pollution in the United States. So overall pollution has been falling in the United States. Meanwhile, because of climate change, we have more periods of intense vegetation growth and then dry spells, which leads to wildfires, including like recently in New Jersey, and even a part of Manhattan it had a wildfire not so long ago. Anyway, we have more wildfires in the United States. That's a larger share of pollution. They make the argument that lots of U.S. counties are exposed to it, and they find really big labor market effects. So wildfire smoke reduces U.S. annual labor earnings by 2%, or $125 billion. Okay, and this is most likely to grow given growth in wildfire exposure. And so they're making a claim which is very surprising to me, but it's a very well done paper, is that the lost earnings effect of wildfire smoke are greater than the mortality costs. Okay, and usually it's the other way around. It's like social cost of carbon, it's the health effects the health and mortality effects in particular that drive the social cost of carbon, not sort of people being a little bit less productive at work. And this is arguing the opposite, is that in terms of economic damages, it's really the labor market. Okay, this is the predecessor paper to the presentation today, looking at these power plants in the state of Pennsylvania. And we were focused in that one solely on carbon dioxide emissions. Okay, so this was totally ignoring local pollution and thinking about how much these firms were making in terms of bitcoins that they mined, and comparing that to the damage caused when we apply a social cost of carbon to the carbon they're emitting. Okay, so the U.S. government in the previous administration had a social cost of carbon around like 190 or something like that, $190 per ton of CO2. And so you can estimate the damages of that CO2 relative to the benefit of mining, and you see that damages are like at least 3 times the private benefit. That was focused on the scrubgrass power plant in western Pennsylvania, which is fine from a carbon perspective, because for carbon it doesn't matter where you emit it. It's a global effect. One of the scarier things that happened during the course of that project is we got a scary letter from the general counsel of Stronghold Digital Mining, telling us to retract our paper, in very sort of legal language. And they had a lot of claims in that letter saying things like Scrubgrass began mining Bitcoin in the fourth quarter of 2021, not back in 2018, as you guys said, blah, blah, blah. So this was like a referee report, but like from a lawyer. So like referee reports are bad enough as is, and like you get a legal referee report. That's kind of bad. So we asked Columbia's general counsel. I'm sure they're too busy with other things now, but back then we asked Columbia's general counsel, can we like respond to this? And they said, okay, yeah, you can respond, but show us your response first. And it was like a lot of fun to respond to it, because it was a referee report, but it was also like the worst like quality referee report we'd ever received. So it was easy to say things like, well, this claim about when you're mining Bitcoin contradicts the statement you submitted to the SEC, whatever. So they were just BSing us and trying to scare us off. And so, we did a very comprehensive reply, and we haven't heard from them since. But as mentioned, we did not like approach Scrubgrass to tour them, because I think they probably don't like us. Okay, so that's the background. Now for ordinary least squares. I'm not going to spend too long on ordinary least squares, but I think it's useful for just thinking about when we control for the usual fixed effects and stuff. What do we get insofar as the relationship between pollution and labor market outcomes is concerned? So we have the dependent variable y being hours worked or hourly wage. We have the right-hand side being, in particular, some polynomial function of pollution, like SO2, and potentially NOx and heat input as well. And we're going to control for things like that polynomial in time, right? So a third-order polynomial in day. We'll have calendar month fixed effects. We'll have day of week fixed effect, zip code fixed effects, things like that. So like, your usual OLS sensible regression. We'll divide up results, but I'm actually going to pretty much ignore it here, about whether the OLS variation is coming, before the end of the trough in prices or not. So in terms of tabular regression results, focus on the ones on the all columns 5, 6, 7, and 8. We actually don't see much of a relationship between hours worked and SO2 in OLS, okay? We see a bit of something with heat input. That's how much coal they're shoveling into the power plant. And this is saying when there's more heat input, you work longer hours, okay? Which is perhaps a bit surprising. We can look at wage, subject to the caveat I mentioned before. Again, columns 5, 6, and 7. And we see when pollution from SO2 is high, we have higher wages, okay? So these are a bit puzzling, some surprising signs. Furthermore, if we think about the magnitude, using the fact of what average wages are around $11.50. People work about 6 hours a day. What this is saying is when we have a 1 standard deviation increase in SO2 emissions, that's like a 3-cent increase in the hourly wage, okay? So not only are the signs weird, is like the effects are like minuscule. And we report what we see for heat input as well. So you might ask yourself, okay, why should I go from OLS to IV? Arguably, we could do a better job with the OLS than we're currently doing. One of the advantages of IV is I think it provides a more exogenous variation in pollution, okay? So like if we think about something like confounding from like a weather shock. Like high temperature is going to cause more energy demand because people are going to use more AC. But you can imagine high temperature is also having an effect on my desire to go to work or how productive I will be at work, especially in more outdoors facing industries and occupation. So Bitcoin mining variation is going to help address that, right? Like, I mean, it's the global price. It's not responding to local temperature in Pennsylvania or anything like that. So that's one reason to do it, is just the usual. If it's a valid instrument, then I get a causal effect. Additionally, we may be interested in what's the effect of Bitcoin mining on people's labor market outcomes, right? And so this use of the variation that's solely coming from Bitcoin mining incentives is going to give us that. So the research question is answered by using Z as an instrument. Okay, first stage, probably no big surprises here. In the first stage, we're regressing pollution on Bitcoin variables in the same set of time controls. I'll sort of skip ahead a little bit in the interest in time. So this is our first stage regression results for Northampton, looking specifically at Northampton. We're looking specifically at Northampton because that's the one where we have the pollution monitor nearby. So the first column here is telling us that for every ton increase in SO2, sorry, try that again. For every $1,000 increase, I knew I had to pause there. For every $1,000 increase in the price of Bitcoin, SO2 goes up by 0.09 tons, okay? So that is useful as a sort of gut check on whether power plants are responding in the expected direction to Bitcoin mining incentives. If you look at the F-stat, that's an F-stat of around 44. If we're interested in how does that output from Bitcoin mining affect pollution in the broader neighborhood, the second and third columns are the pollution concentrations from the EPA monitor. And what we see here is the same thing, is that when Bitcoin price is high, that EPA monitor that's 7 miles away is also showing an increase. And actually the F-stat for the EPA monitor is even higher. It's more like 51. Okay, so there's a tight relationship between Bitcoin price being high and the air quality in the neighborhood as reflected by sulfur dioxide emissions and their concentrations. We can do this for all the power plants. You've already seen it for the Northampton column. As I alluded to before, Panther Creek tends to be paying a bit more attention to the hash rate. So when a lot of other people are mining, they sort of dial back their activity. Scrubgrass is kind of weird in the earlier period when they were supplying electricity to the grid. So for Scrubgrass in particular, we're going to focus on like the last year of their activity when they're a dedicated Bitcoin miner, and that sort of makes them behave as we expect them to behave with respect to Bitcoin mining incentives. We did that separately for each of the power plants. When we combine all those power plants together in this first column here, we get similar point estimates to the ones that you saw for Northampton, and now our F-stat is up to like a more comfortable 88 or something along those lines. We can play with other things like allowing for hash rate to matter or allow for interaction like of a dummy and the prices. You see our F-stat falls when we do that. So like the simple quadratic specification and price where we have the same coefficients across the different plants is what the regression seems to like the best. And that's what we're going to go forward with, is price and price squared as the instruments. And that's good from an over-identification test perspective as well. When we use hash rate and price, the over-identification tests get a little grumpy. You might be interested in sort of where the relationship peaks in terms of Bitcoin price. If we use cubic time trends, then we have a peak around the 80th percentile of Bitcoin price. Whereas if we use the year-month fixed effects, then we have a monotonic relationship in the Bitcoin price, which is maybe a little bit easier to interpret because it's closer to linear. In the IV, no big surprises here, I don't think. We have, we're going to be regressing our pollution on the Bitcoin price instruments, and then we're going to be regressing outcomes on those instrumented pollution values, and we can play around with a different set of fixed effects, whether we have zip code fixed effects or not. What do we find? Okay, so like minor drum roll here. When we have all of our plants together, we first show you the OLS relationship. The OLS relationship was not statistically significant, and then the point estimate is 0.005. When we're doing the IV estimates in column 2, and this is looking at how hours work respond to sulfur dioxide emissions, we see people are working fewer hours when sulfur dioxide emissions are high when using price as instruments for how much pollution there is. So let's talk a little bit about those magnitudes. Northampton and Panther Creek emit, nearly 1 ton of sulfur dioxide per day, and with a max of 6 or 7 tons per day. So on average, that's about 5 minutes less of work per day. If you go to the max, like a really bad day of pollution from Northampton, Panther Creek, that's about a 10% or 40-minute reduction in the amount of hours worked. If we go to scrubgrass, because scrubgrass has a much higher average and max, then we have some really large effects indeed. We have like a 16-minute reduction at the mean and a 50% reduction at the max. So it's quite some substantial effects estimated for scrubgrass, but this is Western Pennsylvania where there aren't a lot of people. We can stratify these average effects across the different industries, and what do you see? You see, well, first, maybe pay a little bit of attention to like the confidence intervals. As you saw in the sample descriptive statistics, food and beverages is the most common industry. It has the smallest standard error, and so we're seeing, point estimate around minus 0.2, something like that. So reduction in hours for a 1 ton increase in SO2, and some larger negative effects as well. Interestingly, we find positive effects for both healthcare services and social assistance. Social assistance is also primarily driven by health as well. So in the more health-intensive things, we actually see an increase in hours worked, suggestive that there are more people requiring health aid in clinics, in hospitals, and that sort of thing. I was a graduate student at Berkeley, and Michael Greenstone was a postdoc at the time. One thing he told me, which I honor here, is there should always be one point estimate that breaks your heart. Like that just didn't get the memo, that does not make sense with your priors. I have no idea why auto maintenance has a positive coefficient. I cannot tell a story for that. We will dig into it. Like somebody suggested when I gave this talk at Chicago recently, that maybe people have more traffic accidents when it's more polluted. I have no idea. We'll look, but it could just be inexplicable. I don't know. Okay, so but the broadly speaking, the heterogeneity by industry accords with what we might think. Now let's look at wages. We don't have wages for everybody, so when we focus on the subsample with wages, what do we see? We see a reduction. Let me try that again. When we look at the subsample with wages, we see a reduction in hours worked that's smaller, 0.074 in absolute value relative to the overall minus 0.105. Okay, so a more muted hours response in the subsample with wage data. But when we look at the subsample with wage data, we can see how much hours of work changed by subsample, okay? And we can look above the median wage or below the median wage. And the striking thing here is that hours response is really coming from those with below median wages. The point estimate there is minus 0.39, okay? So multiply, that's roughly 4 times the overall effect. So now we're really having some large effects of the Northampton. You don't have to go to Scrubgrass. You get large effects for the Northampton power plant. So we already had like a low wage sample because we're looking at hourly workers. We're saying within those hourly workers, those people that are the most impacted in terms of hours are the low wage within the low wage. So it's a real EJ story. In the interest of time, I'm gonna sort of skip ahead a little bit. Maybe it's not so surprising when we run wage as a dependent variable because there's this differential response in hours by whether you have high and low wages. More of the low wage people are coming out when pollution is high. So if you look at wages as a dependent variable, they actually go up. And that's, I think, the compositional effect of having a differential response from the low wage people. Event study analysis. So I'll go like sort of 2 minutes on this. This winds up being kind of underpowered, but this is showing you over time emissions from Northampton in terms of NOx and in terms of SO2. And we're just drawn to this because there are periods of it being off and it being on, and we could sort of stack up those big spikes and come up with an event study. We can combine that with Northampton, Panther Creek, Scrubgrass all together, and you can get some like really beautiful event study pictures. That said, when we do the event study, we're only using a small subset, like 10% of our days overall. So we're pretty underpowered when we do that. So we get some sloppy estimates on hours worked. They go as we'd expect, but the precision is reduced. So I'm going to skip past that. But that was another thought for identification. Another one we had is Bitcoin halving. When they reduced in April 2024 the amount of Bitcoins you're rewarded for executing the transaction, it went from 6.25 to 3.125 Bitcoins. So discontinuously, the incentive to mine Bitcoin changed in April 2024. And we can show that, well, we'll go to this one. Power plant emissions fall with halving. They were mining less shortly after halving. And if we look at hours worked, then it looks like hours worked increased at halving. So that's just using one event, but one particularly important event in the incentive to mine Bitcoin. Okay, so in my remaining like 10 minutes before questions, the question for you here is, we can look at the distribution of F-stats of all power plants in the United States and how they respond to Bitcoin mining incentives. And if we do that, we come up with 41 other power plants with really juicy F-stats, like F-stats greater than 88, okay? So all of these 41 power plants are like very suspicious of mining Bitcoin. So one direction we could go with this project is to generalize this to like a lot more power plants. And we haven't done that yet, but that's somewhere very naturally we could go. Now, not all these power plants are going to be Bitcoin miners. Like some of them are going to like have wrong signs on price. You know, it's just going to be false positives and that sort of thing. So we need to be wary of that. But that's one direction we could be heading next and looking at all those local populations surrounding whatever the 20-odd power plants that survive that scrutiny. So I'll skip past this. We had an undergraduate RA who then read up on all those power plants and was able to say, okay, she really thinks these 12 are definitely mining Bitcoin from the news coverage. Okay, so very quickly on the atmospheric transport model, the EPA has did some really nice work on modeling how emissions go from a point source to to farther removed locations. It's combining very detailed data on meteorology and land surfaces, okay? And so this is just showing a bunch of the different data pieces that come together, including the SEMS data, the Continuous Emissions Monitoring System data, which is the data we're using to say in each hour how much SO2 is being released by Northampton, Scrubgrass, and Panther Creek. And so doing, you come up with some really neat estimates of concentration levels and how they disperse in space. So depending on the date considered, so the first one being February 11th, 2022, the wind was blowing, towards the north from Northampton, and that's where you didn't want to be working then. Whereas on April 30th, in the middle panel, it was blowing to the northeast, and it looks like, with higher emissions coming out of the Northampton facility as well. So we have much higher concentration levels, along a trajectory, a fairly linear trajectory out from the power plant. And then come, looks like August of 2023, the wind was blowing down to the southeast. So that's all the variation we hadn't been using because we were just using radial distance around the power plant. But we actually have enough data and modeling to say where exactly those emissions are going. I don't know if people have used these atmospheric transport models. We were originally using the high split model, which is the one that's most commonly used and has been used by other folks in the Sustainable Development PhD program, looking in particular at Korea, right? Like how health in Korea responds to pollution emissions from China, North Korea, and from Korea itself, is using the high split model in a very, I think, a cool and knowledgeable way. High split is actually very good at long trajectories, okay? Air mod is better at the short trajectories, which is why we're using the air mod. And what we're going to be using in terms of these final regression results is not only the Bitcoin price, but whether there's wind alignment, okay? So we're going to be measuring the angle between the predominant wind direction at the power plant and where the centroid of the relevant working zip code is, okay? So we're going to construct all those angles to all of those zip code centroids. If your trigonometry is as rusty as mine, then maybe this diagram is more helpful. That we're taking the cosine of the angle. And so what we see in summary is what's over on the right, is that when you are directly downwind, then you're hit with a 1. Oh, 1 times the emissions, right? And if you're moving towards crosswind, that's the vertical line, that's a 90-degree angle, you come down to 0, okay? We don't think you're getting hit with it anymore if you're crosswind. And everything crosswind or to upwind, you get 0, okay? So now we're only using high prices when you're downwind, and we're hitting you with more of those prices when you're more directly downwind, okay, as makes sense. That's sort of the beauty of what the cosine function is doing. All right, so we can do our first stage where we're regressing sulfur dioxide on wind alignment interacted with Bitcoin price. And we can play around with what fixed effects we use. And we're going to do something especially crazy here just because we can. We can also kill off the Bitcoin variation, have a dummy for every day, and only use that variation in where the wind is blowing to. But before talking too much about that, what do we see when we look at the first stage of how SO2 concentrations, as estimated by AirMod, respond to price and being aligned with the wind? Well, we have across all plants a fairly healthy F-stat of 47, and then when we look at Northampton in particular, our sort of preferred, if not declared, Bitcoin miner, we get like the record-breaking F-stat of the day of 333, which we feel pretty darn good about. So using that specificity of only thinking about pollution being higher when the price is high and you're downwind really, really seems to add to our the precision of our first stage estimates. Okay, and then what do we get when we do the instrumental variables? So this is a slightly messy table. Let me try not to butcher it too badly. So we have two OLS columns and two IV columns, okay? We're looking at the impact of SO2 as measured by this AirMod model. So this is not emissions at the stack. This is estimated emissions at the zip code where people are working. What we see when we do that, so this is a different measure of pollution than the emissions we were looking at before. OLS is smaller than IV, okay? And we should pair the first two columns and the third and fourth column together with each other because they have very different sets of fixed effects. In the first two columns, we have year by month and day of week fixed effects. So fixed effects more similar to those that we used in the non-AirMod results that I showed you earlier. And we see OLS is actually now behaving, right? OLS was not behaving before, but when we improve the measurement of pollution coming via AirMod, we actually get the same sign as the IV and consistent with the earlier results before. So improving that measurement seems to have sort of won the race against the confounders in terms of getting us closer to the right estimate. But as people often see with IV results, and sometimes for different reasons, the IV point estimate in column 2 is way bigger than the IV estimate in column 1. That said, this SO2 measure is not the same SO2 measure as before, so we can't compare this point estimate to the previous one. When we account for the difference in means, this impact estimate is actually fairly similar to the one we found before. Okay, so that's it for the first two columns. When we're using the year by month and day of week fixed effects, we have a very robust negative effect on hours worked in response to greater SO2. And when we pin it down to being SO2 that's coming from Bitcoin variation, we get the large negative 1.4 coefficient. When we go to the next two columns, we are doing this crazy thing, and it was I who suggested it, and nobody argued with me, but that doesn't mean it's a sensible thing to do. It's where we have a fixed effect for every day. So 1,034 fixed effects. So we're no longer using day-to-day variation, okay? What we're using is like the differential of where wind is blowing within over time, okay? And when we do that, we get a larger OLS coefficient, and we actually get the largest IV estimate, okay? And that's just using this variation from AirMod in wind speed, wind direction, and topography of sort of how it swirls around in response to hitting land and that sort of thing. But on the whole, when we're using the AirMod concentration data, which are the sort of the best data that we have, we see this really robust relationship of fewer hours worked when pollution is high. Okay, so in terms of magnitudes, 1 standard deviation increase in SO2, about 1% less work. If we go to the maximum, then it's about 1 hour. So when you have a really high pollution day, 1 hour reduction. Okay, so let me quickly wrap up and leave a couple minutes for questions. We are still developing this atmospheric transport aspect. The results I showed you were literally run within the past week. We have only used the angle, like the angle of attack of wind at this point, but we have other instruments like wind speed, et cetera, that we could use as well. So how to thoughtfully use those instruments, and sort of in the back of my mind is, can we use some of those instruments to pin down demand versus supply responses for labor, to be able to say something about this is labor supply as opposed to here's just an effect on hours worked. Additionally, as I've mentioned, we can find a lot more Bitcoin miners and extend the analysis to them. We don't need that from a statistical power perspective, but it's something we could do to increase generalizability. We also have purple air monitors. So those are indoor air quality monitors that many consumers have just because they like to know the indoor air quality. We haven't analyzed those, but we could say what's the impact on indoor air quality where people spend most of their time. And your suggestions as well. Okay, so to close, what do we find? We find Bitcoin mining has a negative externality on very low wage workers in the state of Pennsylvania. This negative externality piles on top of the externality that we already knew about, which was the carbon aspect, which is a global negative. Now we're showing you there's a local negative as well. And I think this has first order environmental justice implications. What's really frustrating to me personally is there is no need for this to occur, right? There are other ways of generating scarcity in cryptocurrencies rather than leveraging the cost of power. Right now, cost of power is being used to generate scarcity, and Ethereum used to have a costly proof of work mechanism, which they switched over and reduced energy consumption on their network by 99%. Okay, so if we could talk Bitcoin into not using this algorithm, we could eliminate this externality. And still have those crypto mining benefits. It's not trying to kill crypto. It's just their means of creating scarcity has a large negative externality. And then circling back to what I touched on at the beginning, renewables are definitely growing and they're economically much more competitive over time. But there are all these new demands on energy. AI is going to be much bigger than crypto, to be frank. So to the extent that we're using more fossil for AI as well, but also just developing countries are going to be using more energy as well. You might think that natural gas is that's the bridge technology. And I have to say just 30 seconds of bad mouthing of natural gas, because natural gas is 30 to 80 times more potent a greenhouse gas than is CO2. If you have modest leak rates through the natural gas supply chain, you actually have similar carbon forcing effects to coal as with natural gas, especially over the next 20 years. So if you get above a 4% leak rate, then natural gas is worse for near-term climate change than is coal. Okay, and I don't think that's well recognized. People haven't known how high the leak rate is, but now that we have these satellites, it is that high. If you look at estimates over time, it is that high. So don't be comforted by burning natural gas. It's up there with coal in terms of climate forcing. So I wish I could end on a happier note. We have these large negative externalities. Fortunately, we have beautiful new data sets in which to understand those externalities. I thank you very much for inviting me today and for your attention during this talk. And I have 5 minutes for questions. Sorry, it's not longer.
Questions?
Hi, my name is Owen Chung, and I'm actually from Pennsylvania, so this is very interesting. I was kind of curious what the mechanism by which air pollution is linked to changes in hours worked. I assume it's largely explained through health, but if it's kind of I'm curious if it's a short-term effect or a long-term one, because I assume that acute exposure to air pollution is not explaining most of the health outcomes, the negative outcomes related to air pollution. Thank you.
Yeah, and unfortunately, that's an excellent question, and one that I don't have a great answer for. I mean, I think like many comparably well-identified studies, they're often sort of bad at the mechanism part, and in the absence of having the hospital discharge data or something like that, where we can see, it's respiratory admissions that really respond, or it's people with asthma, right? For example, that really, those are the workers that now have to work less when pollution is a little bit higher. My guess is it would be something along the lines those lines, but in the absence of those health data, it's tough to know. But you've also raised the other question, which is, we're looking at the very short run, hyper short run effects. We can think about the total effect is going to be the short run effects plus the medium term effects and so forth. The Rima Hanna Paulina Oliva paper found it sort of a week later. So I think one natural thing, and maybe something we very much should add to our to-do list, is if we, especially with the benefit of having the atmospheric transport variation, maybe we can fall out of love a little bit with this daily variation and go to like the weekly and say, okay, on this week, the wind was blowing this way and that sort of thing. And then we can think about like this week's pollution, last week's pollution, week before that, and how that affects. And so that would be a way to sort of efficiently use all of the power of our instruments to sort of identify not just this immediate effect. And we ran to the immediate effect because it's sort of like, that's where our identification is best, but like we want to know the total effect, and that's exactly what you're saying. And I think a benefit of this sort of newer part of the paper is I think we'll be in better shape to consider not just the daily acute response. Yeah.
Hello, thank you very much for your presentation.
Thank you.
It's really interesting. I am from Paraguay, from Latin America, and we currently have the second largest hydropower plant in the world. We share it with Brazil, which we have a surplus of electric power. So I think I didn't quite get, but I think you relate SO2 emissions with the emissions of the carbon power plant, and then the labor.
Yep.
Group. But I'm interested if we change the source of electricity as a hydropower plant, for example, for mining the bitcoins, it will still affect the hours work and the wage. And if you can give me your opinion of, do you think this is a good way, an opportunity for Paraguay to enter the cryptocurrency minery or making wealth out of?
So thank you very much for that. And sorry, what's the source of power for the
Hydro.
Hydro, yeah. So I think that's really interesting. So it's been advocated by Go Jin-he, I think in Chinese, that like China should be using its excess renewables to mine Bitcoin, okay? And there is curtailment, right? Like you have this excess renewable energy during certain periods, right? And why not, if it doesn't have another use during that period, use it to Bitcoin mine instead of using fossil, right? And I think there is a logic to that, but what it also sort of highlights in my mind is if we had better storage technologies of electricity, right? Then what we'd want to do is use periods of excess renewable energy, store that, and then deploy it, when demand is high or when we can substitute out from fossils. And so I think whether it makes sense to do that depends on sort of like the availability of storage options where we could actually offset fossil emissions or not. And so I think it really depends very much on the context, whether it makes sense. And I was actually giving a talk at Tokyo University yesterday. In Japan, their largest power company, during periods of excess renewables, it mines Bitcoin. So there's plenty of precedent for that, but I guess thinking through the counterfactual of what would be done with that electricity in the absence is the sort of key thing to do.
Yeah, for the sake of time, Islam will be the last question.
Thank you for your informative presentation. I'm Ismail from Egypt. For the slide about the relation between prices and air pollution,
Yep.
It showed the price is positively correlated with the air pollution, but for price square, it's negative. Price square, I guess it showed that it's a non-linear relation, and after a certain point or threshold, turning points, the pollution starts to decrease. Is it related to the trading prices for the Bitcoin? And if like that, if we look for the chart, if there is a lot of turning point of the prices or the study on certain period only. And I have another question about subsidies. Does USA subsidizing the renewable energy power generation for the mining process or all type of power generation? Because all power generation resources, it's a sustainability dilemma, and we are energy policy student and curious about that topic. And thank you.
Okay, thank you. Those are two excellent questions, and I'll answer them very, very quickly given the time. So yes, you're quite right. So it is the case that through 80% of the variation in Bitcoin prices, we have positive, but then it tails back at the top when we have that quadratic function. But that's when we have the cubic in time. If we have the month by year fixed effects instead, then it becomes fully monotonic. So I'm not so worried about necessarily having to explain why it sort of is backward bending at the top, because it's not robust to how we control for time. We can get the monotonic relationship. Sorry, remind me the second in 3 words.
Subsidies.
Oh yeah. So in the U.S., yeah, we subsidize under the Inflation Reduction Act. We switched to like subsidizing renewable energy. But if you look sort of at what's currently done with fossils in general, the fossil subsidies are much greater than the renewable, and the implicit fossil subsidies are much greater than the explicit renewable subsidies. So yes, we subsidize energy a lot, and the U.S. is now the #1 LNG exporter in the world. So like, yes, we do that like crazy, but we're still tilting the scales towards fossil on that. Yeah.
All right, let's give him a big hand.
Thank you so much.